Hello student. Today I am going to cover up process states, CPU schedulers. Basically, these schedulers can be classified into three types: long-term scheduler, short-term scheduler, and mid-term scheduler. Then after dispatcher, and last topic is the CPU burst versus IO burst. So we will discuss one by one. Firstly, process state. Whenever a process bring up into the main memory, it may reside in any one of the following five states. These states may vary on the operating systems. In general, there are five states. So a process which is executed by the processor may remain one of the various states. These states are new when a process is being created, running state when the instructions are being executed, waiting state when a process is waiting for an event such as input output completion or reception of the signal, ready when process is waiting to be assigned to a processor, and last one is the terminated state, or it is also known as the halted state. The process has finished its execution. So it is the general diagram for the process states. New means it is a hard disk. This is the pool where the all programs reside. A new a new file is being fetched from the hard disk or the pool data and brings up into the main memory and put up into the ready queue. From the ready queue, the process is handed over to the processor to execute. If it completes its execution, then it goes to the terminated state. Otherwise, suppose that I am using the round robin scheduling algorithm and there is a 2 millisecond time slot is allocated to each process. After execution of the process as a 2 second, this process goes to the ready queue again and put it into the backside. A new process from the front of the queue is handed over to the CPU for execution. If that process requires an input output, for example, I am using a program or executing a program that requires two numbers as an input, and it will get the output of those two numbers. So it will wait for the, suppose that program get executed and it requires the input, the first number. So when it requires the input, that means it is waiting for the IO. Means from the keyboard you have to give the input, and corresponding to that, then after it will take the second number. Once it requires an input output, so it goes to the waiting state. If suppose that you are not in front of a screen, so it will wait until you will not press first number. As you press the first number, it will get to the ready state, and then after it will, when its turn comes, it will put up into the running state. Then after it will execute the next line that requires the another number, so it will again goes to the waiting state and wait for the input from the user side or any another input device also. Suppose that I am using the two addition of two numbers, so I will enter the second number. It will again go to the ready queue, and when the its turns comes, it will goes handed over to the processor, and processor will execute. And then after summing the two input number, it will print the result and get terminated. This may be possible when a process is executing a higher order process may comes into the memory. So immediately that process will get interrupted and the higher order process will be handed over to the processor. So this process is running continuously. So this diagram we can easily explain with the help of the this animation. So here a new process is admitted and enter into the ready queue from the back and brings up into the front, and then after it is handed over to the CPU or processor for executing. The processor is executing the process. Meanwhile, another process is entered into the ready queue. When it's turn finished up, suppose that the process or the processor is higher order process, so it will this process will get interrupted and put it into the ready queue from the backside, and the higher order process is handed over to the CPU for the execution. While higher order process is executing, the another process brings up into the main memory. Suppose that now the higher order process requires the input output from the user. So it is goes to the waiting state, and next process is executing. The waiting state in the waiting state it requires the printer. When the printing has been finished up, it goes to the ready queue. The process is executing, and the executing process has been terminated, so it will goes to the halted state or the terminated state. Now the higher the a process from the front of the queue is removed and handed over to the processor. So this process will continue until all the process will not get terminated. So CPU will busy in execution of the process. Now the last process is only this one, so it will continue its execution. When it will get completed, it will goes to the exit state. Now all process has been bind up. So this is the basic diagram for the execution of the process, how the process executes. So I have explained through the animation also. Now, coming on the schedulers. During the life cycle of a process, there are three types of the scheduler: long-term scheduler, short-term scheduler, and medium-term scheduler. When a process is brings up from the job pool to the ready queue, this is the responsibility of the long-term scheduler. Why it is known as the long-term scheduler? Because it takes longer time to bring up from the to bring up a process from the hard disk or the job pool to the ready queue. That's why it is known as the long-term scheduler. It is also known as the job scheduler. A process migrates among various scheduling queues throughout its lifetime. The operating system must select for scheduling purpose the process from these queue in some fashion. In general, it is known as the job queue. The queue is stored in the linked list. In the linked list, it contains the pointer of PCB of the first and last process waiting in queue, and PCB of one process contains the pointer of another process. Means process 1 is there, then after it will contain the address of the next process, then it will contain the next process. So there is a queue type structure is there, linked list type structure is there. For example, this is the PCB1 process P2, this is the process P1 PCB, and this is the process P0. So P0 is the first process, so it is linked with the previous one, and it is linked with the previous one. So this type of structure is followed by the schedulers. So I am going to discuss long-term scheduler. The processes are spooled in the mass storage, typically a disk where they are kept for the later execution. The long-term scheduler or the job scheduler selects one of the process from the pool and loads into the memory for the execution. That we have discussed. It will load one process, new process from job pool to the ready queue and brings up into the memory. The long-term scheduler is responsible for transferring a process to the ready queue and making the ready it for the CPU assignment. Since the processes are not rapidly created, that's why it is known as the long-term scheduler operates less frequently. Means process will brings up one program is bring up brings up into the memory. It will continue to execute. It is not necessary to bring up the entire process again and again. For example, if you are using if you are watching a movie, in that case that movie will brings up once in the main memory. Short term scheduler. The short term scheduler is also known as the CPU scheduler. Selects a process from the ready queue according to the type of scheduling implementation by the operating system. After selecting the process from the queue, it assigned to the CPU or the processor. Means once a process, a number of processes may reside into the ready queue. For example, this is the ready queue. Here are process number 1, 2, 3, and 4. So it is one ready queue. This may be possible. There are more than one ready queue. 1, 2, 3, and 4. So there are 8 processes in 2 ready queue. This is the R1 ready queue 1 and this is the ready queue 2, R2. The ready queue 1 has the higher priority than the ready queue 2. In that case, firstly, all processes from ready queue 1 will be handed over to the CPU for execution. Once this ready queue has been wind up, then all processes have been finished their execution. Then after ready queue will get start to hand over to the CPU or the process in the ready queue will start to get execute. So it depends on the priority of the ready queue or the implementation of the processes by the operating system. Here we are assuming only there is only one ready queue. So as I have seen in the diagram, so here is only one ready queue. So processes are fetched from this ready queue and handed over to the processor. But these ready queue may be more than one in number depending on the implementation selected by the operating system. So coming on the next. After selecting a process from the ready queue, it is assigned to the CPU. Since the CPU rapidly switches from one process to another process, therefore short-term scheduler operate more frequently because there is a migration of the context switching take place from one process to the another process. On the most of the system, good user response time is more important than the efficient processor utilization and may necessitates switching between processes frequently, which will increase the system overhead and reduce the overall process throughput. Whenever I will migrate from one process to another process means processor will migrate from one process to another process. It will not perform any useful work during the context switching. So that will be overhead. Along with that, the throughput means amount of work done will also get reduced. When a processor will remain idle, it will not perform any useful work, so automatically throughput will get decreased. medium-term scheduler. The key idea behind the medium-term scheduler is that sometimes it can be advantageous to remove the process from the memory for and from active con- contention for the CPU, and thus reduces the degree of multiprogramming. So we can say medium-term scheduler is responsible for controlling the degree of multiprogramming. How many program will reside in the main memory? For example, here it is a main memory. This portion is taken by the OS, and here are three processes P1, P2, P3, P1, P2 and P3. These are the three processes. P1 is executing, P2 is executing, and P3 is also executing in the sequential order. Now, suppose that P1 requires a printer, but printer is not available, printer is busy somewhere. And a new process want to bring stuff into the memory to get executed. So it is better to remove this process from the main memory and swap it out into the secondary memory, that is your hard disk. So this process is swapped out from the primary memory to the secondary memory. By this mean the medium terms controls the degree of multiprogramming. Although here the degree of multiprogramming will remain same, that is the 3. Degree of multiprogramming is how many programs are remaining in the main memory. So at present here, although the program 3 will remain, lekin it will swap out one program so that another program can be bring up into the main memory from the secondary memory. So this is the process by which the medium-term scheduler controls the degree of multiprogramming, or it reduces the degree of multiprogramming by transferring a process from primary memory to the secondary memory. This scheme is known as the swapping. More precisely, it is known as the swap out. There are two processes, swap in and swap out. Swap in means bring up a process from secondary memory to the primary memory, and swap out means removing the process from primary memory to the secondary memory. Now, there is a comparison also possible in terms of schedulers. Long-term scheduler, it is known as a job scheduler. It is also known as the CPU scheduler. This is known as the swapping scheduler. It selects a process from the pool and loads into the memory for the execution that we have discussed. It selects the process listed in the ready queue and hand over to the processor. It swap out or reintroduce the process, that is known as the medium-term scheduler. It controls the degree of multiprogramming. It also controls the medium-term schedulers also controls the degree of multiprogramming, but it does not have control or very less control over the degree of multiprogramming. Speed is lesser because only once a process is brings up into the main memory, then after CPU scheduler is responsible for handing over the process to the processor again and again. That's why it is faster among these two, and mid-term scheduler or medium-term scheduler speed is in between the long-term scheduler and mid-term scheduler. Now coming on the dispatcher. Sometimes the question is asked, what is dispatcher? So dispatcher, we can understand this by the better understand by the this diagram. A job is selected by the short-term scheduler. Now it is the responsibility of the dispatcher to hand over that process to the CPU. So after selecting a process by the short-term scheduler, the dispatcher get activated. So here the dispatcher is a module that gives the control of the CPU to the process selected by the short-term scheduler. Means once the process is selected by the short-term scheduler, it will hand over the control, or we can say it will hand over that process, that selected process, to the processor. So for this, it requires the switching, means from whatever the process is currently executing, it will remove, it will save the uh, information of that executing process, or we can say the PCB, to the main memory, and allow the register to get free, and then after load the new process PCB into the memory and their contents into the register, and content of that particular process into the register. So jumping the proper location in the user program to restart the program. The dispatcher should be fast as much as possible, since it is invoked during every process switch. The time it takes for the dispatcher to stop one process and start another process is known as the dispatch latency. Means stopping the process, saving the content of the PCB into the main memory, and loading the new process content into the register. This time is known as the dispatch latency. So this is the diagram that I have already explained now. CPU IO bus cycle means there are two type of process. When a process is requiring or executing the CPU or spending more time to the CPU, known as the CPU burst, and if a process spends more time with the input output, then it is known as the IO burst. The success of the CPU scheduling depends on the an observed property of the process. Process execution consists of the cycle of the CPU execution and IO wait. The process alternates between these two states. The process execution begins with the CPU burst and followed by the IO burst, which is followed by the another CPU burst and then another IO burst. So a better mixture of the processes means IO burst and CPU burst must be there. Suppose that all processes are the IO burst, means spending most of the time with the input output, waiting for the input output. So in that case, CPU have to remain ideal most of the time. So this is not a good sign because the throughput will decrease. So we can say there should be a good combination of the CPU burst and IO burst among the processes. Finally, the CPU burst ends the process with the system request to terminate the execution. Here, the CPU burst load is load store, add store, read from the file. So this is known as the CPU burst. And then after IO burst, it is waiting for the input output. For example, waiting for the printer. Then after store, increment, index register, and write to file. Then as it has to write the file, it means it has to wait for the IO. Then after again CPU burst, load, store, add store, read from file. As it want to read from the file, it is again waiting for the IO. So this is a cycle, means CPU burst, IO burst, CPU burst, IO burst, and this process will continue and ends with the CPU burst. The question may be asked for the discussion: what do you mean by scheduling queues? How many types of scheduling queues are there? Com- Compare the process state diagram with the Unix process diagram. As Unix process diagram has the 9 states, here generalize has only the 4 states. How a process bifurcates or created, in general, a process is created with the help of the a system call that is known as the fork, fork. So how it take place, differentiate between various type of the CPU scheduler, how midterm scheduler controls the degree of multi-programming, how dispatcher is differ from the short-term scheduler, etc. So these are the questions for the discussions. Thank you.